Hi, welcome everyone to Alum at Alma talk. Today's speaker is Dr. G. Ramakrishna. He works in the CS department at IIT Tirupati. He has, prior to this, he has worked on at Triple IT CCT as well as Microsoft Hyderabad. He finished both his research degrees from our department, working with Professor Narayan Swamy. And he is one of the few people in India who work at the intersection of theory and systems, in particular graph algorithms on the theory side and parallel computing on the system side. So today he is going to talk to us about one of such works related to cut vertices in dynamic networks. Thanks, Krishna. Thanks, Rama, for accepting our request. Over to you.
Yeah, thank you, Rupesh. It's of course my definitely a lot of privilege to come back to the same institute and present a talk on one of our recent work. Um, and in fact, I always be thankful to the people from whom I pick up all this, the area of whatever I'm working in the recent days, at least. So the intersection, as Dr. Rupesh mentioned about. The parallel computing part and algorithms part, and many of the scholars and students who are attending this meeting also knowing about the both organizers of these series, Professor Narayan Swamy and Professor Rupesh. And coincidentally, both of them, I took great advice and great learning experience from both of them, especially algorithms from Professor Narayan Swamy and GPU computing and parallel computing, especially from Dr. Rupesh. So I always be thankful for them before I go into my technical talk. Thank you indeed for both of them. So I'll share my presentation. Yeah, hopefully my iPad screen must be clear.
Yeah, it is.
Okay, are slides, I mean, able to see whether slides are moving?
Yes, yes.
Okay, great. Yeah. So primarily this work got accepted in IPDBS 2022 in collaboration with other professors from IIIT Hyderabad, Professor Kishore Kottapalli and Dr. Deep from IIT Jodhpur, and one of my MS student, Chirayu. So I'm sharing this work today, and rather than like a conference style talk where typically a lot of material will be typically covered in 15 minutes to 20 minutes, but rather I'll use some of this conference material with some supplementary material. I'm trying to cover like a teaching style, typically the way we discuss in courses. I'll try to take one small module from this work and try to go in detail as much as possible, but without going to lot more theoretical proofs. I will try to balance between. So this work involves the majorly algorithms on the central part, and the other two parts will be one on the proofs, other one is on the implementation. So this talk, I'll be primarily focusing on algorithm design from parallel computing point of view. So that's the setup of the talk. I'll go to the details, and feel free to interrupt me at any point of time. We can discuss in detail wherever you cannot follow, or any sort of more clarity is required. Please feel free to interrupt and discuss. Rupesh, may I know whether students can also talk or chat or something? That's
Yeah, that is totally up to you.
Yeah, that's, I mean, I would encourage, but in case they have access to mic and everything, in case.
Yeah.
Yeah, sure.
They should be able to. Yeah.
Okay, fine, great. Okay. So this talk I will talk about mostly on, I mean, of course, in the complete work we have cut vertices, cut edges, and biconnected components. How do we dynamically update all these in a given graph? That's the actual work. But in this presentation is concerned, I'll be mainly focusing on cut to vertices. How do we find cut to vertices in the parallel setting? I'll be focusing on this in detail, and we'll slowly touch on all these parts. So these biconnected components problem and cut to vertices problem has very common applications where in many of these problems, many of these graph theory problems like max flow, matching, and in all these problems, one of the first step is graph decomposition, where divide the whole graph into multiple parts and start applying these min vertex cover or matching. All these problems one can solve in the individual parts after we decompose the original graph. So that is the place where these biconnected components and cut over vertices kind of problem is can be treated as an application for solving all these problems. So now let's deep dive into the terminology and things like that. So many of you must be already aware of graphs and so on from your data structures course and graph theory and discrete maths and so on. So a vertex is said to be a cut vertex. If we remove this vertex from the graph, then the whole graph will be disconnected. Such kind of vertices we typically call as cut vertices. And when we delete certain edges, one edge, if we delete this edge, the whole graph will become disconnected. Such kind of edges are called cut edges. And also there is slightly the another bit non-trivial definition called biconnected components, which is very much related to these two problems, where from this graph we try to take maximal subgraph, in a sense where try to take as many vertices as possible and as many edges as possible, and such that the graph what we are forming, you look at any of these graphs without having any cut vertices or cut edges. If these graphs do not contain neither cut vertices nor cut edges, then such kind of components we call as biconnected components. So in this talk, primarily I'll be focusing on cut vertices. Even if you do not follow biconnected components, it's perfectly fine. So let's try to go and look at how do we compute cut vertices in general. So I'll talk about in detail. So the problem statement I'll talk about in detail again. But whereas the model is concerned, the model in which we are working in about this problem is parallel batch dynamic. So that is the model what we are talking about. It is slightly different from RAM model, what people must be aware of from your DAA or design analysis of algorithms course. Where the graph can be changing dynamically throughout the running time of, throughout the execution of our algorithm. So I'll touch upon this slowly. All these keywords I'll introduce slowly and then go to the actual. Before we go to the algorithm, I'll try to define all these terms in detail. So let us look at this graph. In this graph, we have a lot of cut vertices. You can observe very slowly, right? If you remove this vertex, the graph gets disconnected. If you remove this vertex, then graph will be disconnected into two parts. Like if you can see, there are many cut vertices, right? We have this cut vertex, this one, this one, this one. We have a lot of cut vertices. So in this talk is concerned, we are not interested in directly computing cut vertices. Rather, this graph is known for us. Also, we know about these are the cut vertices. Somehow we have computed. Now, when we add some of the extra edges, when we add new edges, or when we delete edges from the original graph, essentially the graph is getting updated. Of course, there are certain models where people can thought of vertices also can be added or deleted, but in this scenario is concerned, we are trying to only allowing adding edges and not even deleting. Such kind of graphs we typically call as a dynamic graphs, where we are typically allowing adding edges and deleting edges. In this example, if you look at after we add these two edges, now if I ask again what are the cut vertices in the original, in the latest graph, right? Cut vertices, all cut vertices can be represented in a form of a Boolean array, where each cell, ith cell denotes whether ith vertex is a cut vertex or not. So this is a Boolean array, simple, whether true or false will be there in this array. So in the problem statement, you can think about G is a graph, and also we know this cut vertices array, which essentially tells us whether a vertex is a cut vertex or not. Then whole graph is known for you, every vertex status also is known for you. Then what are we doing in each iteration, or in within each round? We are going to add few edges. When we add few edges, now the task is we should update this cut vertices array. And finally, in the query time, if you want to know whether a vertex is a cut vertex or not, we should go to, if suppose you want to know whether 3 is a cut vertex or not, go to third location and see whether they're true or false. So our task is majorly now we should come up with a algorithm, or even parallel algorithm to allow all these edge insertions and update this array. So this problem we are typically calling as updating cut vertices dynamically in the batch setting, which means multiple edges are allowed to add at same time. And what is the how do we really change all these, whether a vertex is cut vertices or not? That we have to update in the cut vertex array. So this is the major problem statement. I would request if there are any clarifications required, or is there a way to get? I typically use Zoom. Is there a way to get some responses here?
I'm
much?
not sure. I mean, students can definitely raise their hands, which will be notified to you, but I don't see any poll-related facility.
Yeah. I mean, I typically encourage if there are any, should I go ahead, or any doubts whether students have at this point of time, because only problem statement has been defined. I would typically encourage that. Maybe I'll just take.
So students can send a message.
Oh, is it?
Yes, sir.
Where in chat box is it?
Yes, sir. That
Yeah.
one only.
Yeah, sure, great. Yeah, then in the chat box, people can type "go ahead" means G or something, so that I understand at least few of you are following or not. Yeah. Otherwise, I'll go to anyway the next phase after within a couple of seconds. Okay, thank you. I'll proceed further. Yeah. So in case if you cannot follow sometime, please, we are very few people, we can start interacting in more detail. Yeah. So now let us look at all the breadth of all these wide variety of algorithms, where if we are not doing any updates to the input graph, then such kind of algorithms we typically call as static algorithms. There are no updates. Whereas in the dynamic algorithms, we are going to allow either single update or batch update. Single update in a sense where we are going to do some modifications to the existing graph by adding or deleting either vertices or edges and so on. If we allow adding only edges, if we allow all these additions or deletions by only one vertex or only one edge, then we call single update. If we allow multiple edges to be added or deleted, then we call batch update. And incremental is about where we allow only inserting edges but not deleting. Whereas if we look at decremental model, in which we allow deleting edges alone but not inserting edges. Whereas in fully dynamic, this is what we have focused in our original work, where we allow whether the end user is allowed to either inserting edges or deleting edges, perfectly fine. We'll take some amount of time to update what are the cut vertices in the latest graph. So that's what I mean by fully dynamic. Then coming to the power of the architecture, what we are talking about, again, the algorithm need not be running in a single threaded CPU, which typically called a serial algorithm. The one what we are going to look at today is a parallel algorithm, where in the recent days you see on these multi-core machines where every machine has at least 8 core. 8 core is becoming very common, and 16 core, 32 core depends on your various servers in our institutions, right? So how do we use all these multiple cores and make sure to increase the efficiency, to decrease the running time of the algorithm what we are proposing to solve certain interesting problems such as cut vertices. Of course, if you want to understand this, you can think about even MST or connected components problem, which are popular problems in this area, where certain Kruskal, using Kruskal's algorithm or whatever, MST, but when certain edges are deleted or added, how quickly you update your MST rather than computing from scratch. So this, as of now, in the today's context, we talk about cut to vertices, fully dynamic batch update, and multi-core. That's the setting I mean by the parallel batch dynamic. So now we'll start looking into some past work where, with respect to some of the other works that are very relevant to this work, where each of them are having gaps in one way or other. Where if you look at our algorithm, is the one where we started introducing parallelism and as well as dynamic in nature, right, and also batch updates. Whereas some of the existing works, in some way or other, such kind of scenarios are not captured. So this is what our major contribution in this work. So let's talk about some terminology before I go on to provide you the main intuition behind our algorithm. So once the graph is there, I mean, always please try to recall now what is the problem statement. Problem statement is given a graph. Also, you are known about what are the cut vertices in the given graph. Now we are interested to insert certain edges and wanted to know the latest cut vertices in the latest graph. So I would like to ask some simple question where the number of cut vertices after we add these edges with respect to the number of cut vertices in the original graph, will it be increasing or decreasing? Any quick responses I would encourage. Right, there is a graph, right, and there are some number of cut vertices are there, which means if you remove such vertex, graph can be disconnected. That's what we mean by cut vertices and so on. Now when we add edges, right, now what do you think? Right, some of the existing cut vertices need not be cut vertices after adding edges, so essentially it will be decreasing. That's good. Yeah, so it can be remaining same or it can be decreased. That's the right understanding. Okay, so now let's go to the certain terminology and see how we can compute in the parallel setting. So this is a spanning tree of a underlying graph. So graph is not shown here, only the spanning tree is shown, and these are the edges which we are typically calling as non-tree edges, which are, and these edges are appearing in the spanning, not appearing in the spanning tree, but they are from the original graph. Such kind of edges we typically call as non-tree edges. So when we add these non-tree edges, any one of them, you add this non-tree edge to a spanning tree, then we'll get a cycle. And such kind of cycles we call as fundamental cycle. In this graph, each of them we have each of these cycles we call as the fundamental cycles, whereas this is also another cycle that is not a fundamental cycle. So once you are clear about fundamental cycle, let's move to next notation called uh, the notion of safe vertices. So this is one of the most important intuition come from this idea, where in this whole spanning tree, this vertex x, we are calling as safe vertex, provided if the parent of x is not there, even without going through the parent, x can reach the grandparent. X can reach the grandparent without going through the parent. Such kind of vertices we call as safe vertices. Right, in this graph clearly you can see, right, this is this vertex is a safe vertex. Whereas, yeah, there are interesting examples where little later you will notice that there are unsafe vertices also at some point of time. Even this vertex is, this vertex is unsafe because it cannot reach, there is no grandparent at all. And yeah, so this is what I mean by safe vertices. Then little later we are going to talk about further next terminology where we are going to look at any non-tree edge. For every non-tree edge, we are going to have two end vertices. So for a non-tree edge AB, you look at the end vertices A and B and look at their least common ancestor. Least common ancestor, possibly you must have known from the earlier literature, where you look at their ancestors, their ancestors, their ancestor, and so on. Among all the ancestors of A and B, there are so many of them are common. Among all of them, the one which are closer or closest to both A and B, which we are calling as the least or lowest common ancestor. For the vertices A and B in this graph or in this tree is concerned, for vertices A and B, the least common ancestor will be 2. Whereas for this edge, you look at the two end vertices again, and the least common ancestor for LCA for these two vertices will be go to their parent, go to their parents, their ancestors, and so on, till we identify the lowest common one. And for these two vertices, one will be lowest common ancestor in this example. So now as of now, we have quickly recalled about what do you mean by a fundamental cycle and what do you mean by a safe vertex, a vertex that can reach the grandparent without going through the parent. And further, we looked at what do you mean by LCA vertex. These vertices we call as LCA vertex. For instance, this vertex is not a LCA vertex. This cannot be reached from two descendants, whereas this vertex can be reached from two descendants which are adjacent on one edge, right? So if a vertex is if a vertex is becoming a least common ancestor for certain endpoints of vertices, such kind of vertices we call as LCA vertices. Otherwise, we call as not LCA vertex. Now we are going to look at very important notion. With this, little later, we will try to understand the intuition of our algorithm, the intuition behind our algorithm to compute Kato vertices or to update Kato vertices. We are closer to that. For every LCA vertex in this graph, in this example, how many LCA vertices are there? We have this vertex and this vertex. We have two LCA vertices. For each LCA vertex, we are going to create a graph that's called a graph associated with 2 is called G2. The graph associated with 1 we call G1. These are some small subgraphs that we are going to maintain at each LCA vertex, not for all the vertices, only for LCA vertices. And how are we going to create these graphs? What do you mean by this G2 and G1 and so on? I'm trying to define what do you mean by these LCA graphs. All the children of 2, 3, 4, 5, all the children of 2 are part of G2. Not only 3, 4, 5, even 6, 7, 8. All the children of 2. All the children of 2 are vertices in G2. And all the children of 1. All the children of 1 are vertices in G1. So far, we have seen about what vertices need to be kept in LCA graphs. Now we should talk about how are we adding these edges. That is one of the most important intuition that helps in our algorithm. We are going to add an edge between 3 and 4. We are going to add an edge between 3 and 4 in this subgraph. We are going to add this edge. What does this edge mean? Why are we adding this edge in this graph? This edge denotes that there is a path from 3 to 4 without going through 2. Without going through 2, we have a path from 3 to 4. Then we are going to add this edge. Now, why did we add edge between 4 and 5? Because there is a path from 4 to 5 without going through 2. This kind of edges we are going to add with respect to every non-tree edge. So we look at this non-tree edge, go through the entire fundamental cycle, and we understood that there is a path from 3 to 4 without going through 2. Then we'll be able to add, we should add this edge between 3 and 4. This kind of process, we look at any two children, as long as there is a path between any two children without going through 2. You can ask this question, whether there is a path between 3 and 6, without going through 2. There is no such path. And hence we are not going to add any edge between 3 and 6. Yeah, so at this stage I would like to take some small pause again. If you are not clear about how do you construct these graphs, or if you have any clarity is required on how to create these kind of graphs, small graphs, which we are calling as LCA graphs. All these LCA graphs we are maintaining at each LCA vertex. If you need any clarification, I'm happy to wait for some time, just possibly some few seconds. Okay, yeah. So then I'll try to proceed further. So once we are clear about these graphs, which we are calling as LCA graphs, then the next notion is we further call as, what do you mean by, within these LCA graphs we have a lot of components. The graph need not be connected. The LCA graph what we have constructed so far need not be connected graph. It can have multiple connected components. Now we ask whether each component in these graphs, whether it is safe component or unsafe component. Now we have to define what do we mean by safe component and unsafe component. Couple of slides ago, before few slides, we have seen the notion of what do you mean by a safe vertex or not. If a vertex can reach its grandparent without going through the parent, we call safe. Now in this graph, you can see that 8 is a safe vertex, and whereas 6 and 7 are unsafe. As long as we get at least one vertex in a component is safe, then the whole component we are calling as safe component. In this example, this component is a safe component because this vertex is safe. Whereas this component is unsafe because all of them are unsafe. None of them are safe. Now you can appreciate again in G9, the graph associated with G9, we have all these vertices are there in G9. Right, all these vertices are there in G9, and we have added this edge because of there is a path between 14 and 15 without going through 9. There is a path between 12 and 13, right, without going through 9. We have added all this. Like this, we have created this G9, and in G9 need not be connected, it is disconnected, and now we go to each component and ask whether it is safe or not. And G1 is completely unsafe. G2, this component is safe. In G9, these many components are unsafe, and so on. Now, one of the most important characterization or the theorem what we have proved in this work is, even if you look at the Tarjan's algorithm, which is a very classical algorithm which is available in textbooks, where if you want to know whether a vertex is a cut vertex or not, we typically look at, based on Tarjan's algorithm, we look at low point and some DFS number and so on. That is based on depth first search spanning tree. And there is Slota's algorithm around 2014 and so on. That paper is mainly about BFS spanning tree. Whereas in our algorithm, we are focusing on some spanning tree that need not be either BFS spanning tree or a depth first search spanning tree. In any spanning tree, our algorithm will be working. That's one of the uniqueness in our algorithm. So before going to the algorithm, we talk about what are the most important properties based on what we have seen so far. So if when do we say whether a vertex U is a cut vertex or not? U, whether it is a root vertex or not root vertex, we are going to have two important cases. If U is not root vertex, now we look at the LCA graph associated with that vertex called U, as long as you have at least one unsafe component. As long as we have at least one unsafe component in GU, then U is a cut vertex. Whereas for root vertex, the number of components need to be at least two with confidently we say that the vertex U is a cut vertex. And there is another slightly very trivial condition where as long as the vertex U is incident on a cut edge, then definitely U is going to be a cut vertex. This is a bit trivial to see, very easily one can look at few examples and can convince. Whereas for these two, the complete proofs are part of the paper. I'm not going to the details of the proofs, but rather I'll try to give you the intuition behind why this works and so on. So let us try to look at these examples and see what are the cut vertices and whether really these properties, whether they are holding true or not on this example at least, and get an intuition on why this algorithm works. So in this example, 2 is a cut vertex. How do we say whether a 2 is a cut vertex? Manually, one can observe and see that if you remove this vertex, the graph will be disconnected. This is one component and all this is going to be another component. But how do we algorithmically or using some structural properties, how can we see that 2 is a cut vertex? So let us look at these, the entire LCA graph. These are the LCA graphs. This component in some sense is corresponding to this component. This is what our intuition, right? Why are we talking about all these LCA graphs and so on? Because at a little later stage, whenever we are adding new edges, we don't want to go through and look at whole graph. We don't want to process. We want to process wherever the changes are happening. We want to look at locally only those small subgraphs we want to process rather than processing the entire graph, right? So whenever we so now let's come back again to the intuition on this example. This component in some sense is equivalent to this component, and even this component is some sense equivalent to this component, and this component in some sense equivalent to this component. So in this example, 2 is a cut vertex. And how do we say that 2? Why do we say 2 is a cut vertex? None of these vertices can reach their grandparent. None of them can reach their grandparent without going through the parent. So which means the parent is very, very essential, right? And whenever you, as long as parent is there, then all these people are not orphans. In some sense, they are connected. But once you remove this guy, once you kill this guy, all of them, in some sense, they are orphans. They are not connected to their grandparents, right? So that's the one of the main understanding. So now, how do we quickly tell that all of these are not connected to none of their ancestors, right? In this example, you can see that though it looks like maybe if this edge is not there, you can see this example and very, very clearly understand the intuition. If this edge is not there, then even this whole component will be disconnected when you remove this vertex. Then which means this whole component also will be unsafe. Whereas in this example, because of this edge, right, this vertex 8 is safe in some sense. Why do we call safe? Because from 8 you can reach vertex 1, which is the grandparent of 2, and hence this is a safe vertex. Because of this safe vertex, those 6 and 7 are not safe. Those 6 and 7 are not safe, but 6 and 7 can reach a safe vertex. 7 can reach a safe vertex, and 6 also can reach a safe vertex. Because of and this reachability we have already captured in these small graphs. So what does that mean? 6, though it is not a safe vertex, it can reach a safe vertex. From there, one can go to the grandparent. Whereas 7 also, 7 can reach a safe vertex and can go to the grandparent. 8, of course, it can directly reach a grandparent without going through 2. So as long as a component is safe, because at least one vertex is safe, then this guy can be killed, and there is no worry for all these guys. So that's what I mean by the most important intuition I try to give in this example. And if you're able to follow or not follow, please at least some some responses would be appreciated.
Yeah, so Rama, I think Snehadeep had this question
Right.
that in G2, why are we not connecting 3 and 5?
Okay, very good, very good. Yeah, I'll try to, I'll give on that. Yeah. So in this example, ideally, I mean, the way we have defined, the way we have added these edges, or you don't have to go through really all pairs of the children. Of course, if you look at that way, you can add another edge between 3 and 5, doesn't matter. We can add also. There is no problem. Because if you want to look at every two children and see whether there is a path between every two pair of vertices without going through 2, that is one way of doing. But another way of little more optimization can be, you don't have to really look at every pair of vertices. As long as 3 and 4, they are connected, because of this path we have added this edge, because of this path we have added this edge, then 3 and 5 are already connected, and you don't have to really add one more edge. So in the algorithmic way, if at all you want to really consider which pairs need to be looked at when we are adding these edges, we don't have to really look at all pairs. As long as you look at only these non-tree edges, that will be good enough. So non-tree edges meaning you look at for every non-tree edge, we go through the entire fundamental cycle, and within that fundamental cycle, other than the least common ancestor, look at their neighbors and start adding an edge between those two vertices. So this process we would like to do for both of these edges. Then essentially will be through this fundamental cycle we have added between 4 and 5. If at all there is another non-tree edge like this, we would have added another edge between here and 3 and 5. Otherwise, it's really not required. Hope that makes sense. Okay, yeah, great. Yeah. Yeah, so now given this intuition about what do you mean by safe component, and when do we say vertex is cut vertex, that's the most important property what we have defined. As long as U is not a root vertex, and within the GU, within that LCA subgraph, as long as we have at least one unsafe component, then we'll say U is a cut vertex. This is one of the most important property. Other rest of the two are little easy to follow. So then I'll go to talk about how do we use this property. How do we use this property? Not only for, of course, this property can be used to find all the cut vertices in a static graph. But this property is much more useful not for the static graphs but for the dynamic graphs. When new edges are added, then only locally some structures are going to be updated. Now we have to closely look at only those few local structures in which the changes happen, and we should update cut vertices based on only those few places. So this I'll give an example and a brief about in detail. Yeah. So in our data structure, of course, in all these dynamic data structures, one has to maintain certain things, some information to know if some changes are happened, how should we propagate all these changes to the data structure so that we'll update this data structure dynamically. So in our data structure, we have essentially these are the three parts which are most important parts. One is a rooted spanning tree. Other one is LCA graphs for each LCA vertex. and another one is safe flag. For every vertex, we maintain that whether a vertex is safe or not. So these are the three things that we take care. And in this presentation, I'm mainly focusing on the incremental part and not fully dynamic part. This requires much more time and scope. So I'm focusing on this part, incremental dynamic part, where when we insert new edges, how do we update all the cut to vertices in the original graph? Right? We already know some cut to vertices, and whether they'll be remain as cut to vertices or some cut to vertices will become non cut to vertices. All that we have to look at in detail. So now there is another interesting subroutine. This is one of the interesting subroutine we are using. Uh, we are using in our work, and this subroutine kind of, this is a completely different paper, the other research paper. I'm not going to talk about the complete details of this paper, but I'll talk about uh, how can we use this paper work in our work. I'll talk about at a very very black box level. So you can quickly recall set disjoint union data structure from which is popularly used in Kruskal's algorithm, and the same data structure can also be used to maintain connected components. What do you mean by that? Where in a static graph, a graph is static, and and which means all some kind of edges are already there in the graph. Now we wanted to know whether u and v are connected or not. I'll give you simply two vertices and wanted to know whether u and v are connected or not, whether both u and v belong to the same connected component or not. Right? If you recall some of the fundamentals from data structures codes or algorithms codes, we maintain this representative array, and using this every tree in a forest can be represented using a represented array, as long as, if I give you these two vertices, say u and v, if the representative of u and v, if both are same, then both of them belonging to the same connected component. If both representatives are different, then we'll say both of them are not connected. So as long as you understand this crux, we should be able to use this subroutine in our context. But whereas in our context, we are not going to look at the static graph. We are not going to look at the static graph. Rather, we are going to insert certain edges to the static graph. When we insert these edges to the static graph, the some of the existing components will be merged together. So all that we typically call as updating connected components, of course, in the parallel batch setting. So you can look at this example and easily able to appreciate. This is the whole graph. In the whole graph, we have 4 components, and each graph, in some sense, very closely, we are representing using this representative array. For each vertex, we have a representative. Now, if I want to ask whether 6 and 4 are belong to the same component or not, as long as the parent of, as long as the representatives of 6 and 4, right? This is 6, this is 4, right? If I want to know whether 6 and 4 are connected or not, I will go to 6 and look at their representative. We'll go to the 4 and look at their representative. As long as their representatives are different, then the actual vertices do not belong to same connected component. So now this is the static problem. Now, whereas in the dynamic case, when we insert these edges, right, we already know the graph, we already know the connected components which are represented in this set disjoint union data structure. Now, when new edges are getting added, right, after these edges are added, now we want to again ask query whether 6 and 3 belonging to the same component or not. So we should allow all these edges and combine all these connected components dynamically in the batch setting. And this paper, this work closely we look at from this paper from 2010, right? Of course, this is a GPU work, whereas the one what is required in our context is multi-core, which is shared memory algorithm, but not the GPU algorithm. So now let's go into how we are going to use this as a subroutine in our context. So now again come to the earlier example. I'll try to mention, I'll try to pay enough attention on this example to get the most important details of our parallel algorithm. So far, this span tree is available other than the non-tree edges. And also, these are the cut to vertices because of the earlier already we understood before we added these edges. This was unsafe component, and also this edge was not there, then this component and this component were also unsafe components. And also because of all this we know that 9 and 2 are cut to vertices. Now this is the most important part of the whole algorithm. When new edges are getting added, what are the changes that we should do? So we are going to add this edge and this edge. When we add these edges, then we go to the complete fundamental cycle and get a LCA vertex and look at their children, which means 5 and 6. Now we go to the LCA graph corresponding to 2, which is nothing but G2, and add this edge between 5 and 6. This is what earlier also we mentioned. That's the most important thought. Why are we adding this edge? This edge indicates that there is a path between 5 and 6 without going through 2. So which means earlier this component and in some sense all this component were two different components. Now because of this edge is getting added, we have added this edge, and hence this whole become a single component. Further, we also know that this vertex is still a safe vertex because it can reach the grandparent. Now in this new graph you can observe that there exists at least one safe vertex. And you can recall the theorem what we have proposed earlier, or the most important observation where as long as you have in a component at least one safe vertex is there, then it's a safe component. So which means this is a safe vertex and this whole component is a safe component, then which means I mean that talk I'll discuss it. Yeah, so as long as this whole component is safe, then you can delete this vertex and perfectly fine. Nothing is going to be getting worried, and so 2 is not going to be a cut vertex. Right, now let's look at from the 9's point of view. When we add this edge, what happens? When we add this edge, again we go to the complete fundamental cycle, get a LCA vertex, come to their children and add edge between 13 and 14 in G9, where G9 is associated LCA graph for 9. And what does it mean again? We have added the edge between 13 and 14. It means that the 13 to 14 are reachable without going through 9. Now you could see again whether, of course, these two components got merged. These two components got merged and become a single component. Now you should ask this question whether this whole component is safe or not. Please look at this example in detail, right? None of these vertices are safe. 12 cannot reach 1, 13 cannot reach 1, 14 cannot reach 1. Any one of them cannot reach 1. So all these are unsafe. All these are unsafe, and hence, of course, 10 is safe. 10 can reach its grandparent. None of these are safe. So this whole component is unsafe, and hence 9 is going to be cut vertex. So in our algorithm, now what are the most primary important steps? Now you have understood again the most important, I believe, the intuition. So we have already maintained these all these multiple graphs, G2, G9, G1, all these graphs were already maintained in the previous round. Now when new edges are getting added, what are the most important tasks or steps that we need to perform? When new edges are getting added, we have to call these set disjoint, parallel set disjoint union algorithm to add these edges to the respective graphs, right? Whenever we add this edge, the intermediate step is this edge is the reflection of this edge is nothing but add an edge between 5 and 6. Where should we add edge between 5 and 6? We should add this edge between 5 and 6 in G2, and we also should add edge between 13 and 14 in G9, right? But G2 and G9, this graph itself we are not maintaining. Directly we are maintaining the connected components of G2 and connected components of G9 we have. Whenever we are adding these new edges, we go to those connected components and add these edges and update the connected components. And that's what lies in the other subroutine, what I mentioned, based on the parallel set disjoint union algorithm. So this paper is mostly about, the intuition is about parallel set disjoint union, but our task is more or less, I try to convey based on this example, where you try to add all these edges into these graphs and update the connected components. Once you update the connected components, again you should look at each connected component whether you have at least one safe vertex or not. As long as you have at least one safe vertex, it's going to be a safe component, and if none of them are safe, it's going to be unsafe, and then you should be very clearly say that those vertices will be cut vertices. In this example very precisely, this is unsafe, and hence 9 will be retaining as a cut vertex, whereas in this example, because of this 8, the whole will become a safe vertex, and the 9, in the earlier round it was cut vertex, in the recent round it becomes non-cut vertex. So we have to go to that Boolean array, and we should update the status of this. This is what the most important intuition that we have implemented as a multi-core parallel algorithm. All these, whatever the edges that we are adding, we propagate all this and process all these fundamental cycles, adding all these edges to the connected components. All of them we are doing in parallel. Yeah, so let's go to the certain experiments what we have done. So the algorithm what I have mentioned so far, this is what has been implemented in multi-core, and the kind of data sets what we have looked at in the experiments, where these are pretty much decent large graphs, where some of these data sets, the minimum size is ranging between 1 million to maybe around 1000 million or 1 billion, right? Yeah. So the number of edges are ranging between this and this. These are the kind of data sets what we have looked at. And this experiment is concerned, we are trying to only adding edges, right? Within each round, we roughly added say 1000 edges and so on. When we add these edges and compute all the cut vertices again, then what is the running time of the algorithm what we have proposed with some of the existing algorithms called a static algorithm or parallel I mean, static algorithm is our own static algorithm. The Slotas and Madhuri, this algorithm is about parallel algorithm. We compared our result with both of them, and the speed up is ranging from 5x to 77x. Yeah, so these are the most important results, and yeah, so all these speed up, the credit always goes to the notion of this affected fundamental cycles. Whenever we are adding these edges, we are not really going through the entire graph, rather from the examples you can recall and understand, where only those fundamental cycles which are getting added newly, we process only those fundamental cycles and try to add a necessary edges in only those LCA graphs, rather than looking at the complete graph. So these are the two ingredients that helped us to increase the speed up. And the most important uniqueness about this algorithm, and as well as the characterization, the properties, our work will be depending on only rooted spanning tree, and need not be either BFS spanning tree or DFS spanning tree. And we are closely working on related problems. The same problem, the extensions in the 3 connected and K connected, and as well as the same work, the updating these cut vertices, cut edges, and by connected components in the GPU setting also we are closely working on, but they're in some good shape, not completely solved. We have mostly certain portions we have solved. There are certain challenges still we are working on that. That's the latest update on these lines. Yeah, pretty much from my side got over. And if you have any questions or clarifications required, please feel free. Yeah, thank you.
Yeah, Rama, thanks. I have one question. So when you say that any spanning tree will do,
Right.
um, is there any intuition on whether different spanning trees can give different performance benefits, or what kind of spanning trees might give some benefits?
Okay. Interesting. Okay. Then I would say at least in the current implementations, what we have gone through, where it depends on the height of the spanning tree, because
Nice.
if you look at one of the most important operation is the processing a fundamental cycle.
Mhm.
Right, then as long as the height of a fundamental cycle is more, though we do a lot of parallelism, but it is all depends on how many levels are there in the spanning tree. So possibly for this algorithm is concerned, of course, one can implement in a multiple ways, but this algorithm is concerned, if the height is much more lesser, then the performance will be great.
Nice. Sure. Thank you.
Yeah,
Anyone has any questions for Rama? Anybody wants to ask any non-technical questions to Rama? Because he has gone through the same journey that some of you are going through.
yeah, ideally, I can come and actually wanted to give a live talk in the campus
Oh,
because we are anywhere nearby, but somehow we could not. Yeah, I'll be very happy to come and do that sometime.
sure, we'll arrange for that.
Because always it's much more pleasure to talk with the students from the same institute, right?
That's true. And in a physical meeting, it's always possible easily that the faculty members can go out of the room and you can continue chatting with the students, right?
Of course.
So, all right. If there are no questions, then I would like to thank Dr. Ramakrishna for this interesting explaining this interesting work. And I'm sure that some of you who have interest in probably at the intersection of different areas, you will be able to appreciate this much more. Right? And it's not necessary that you should always be working in a particular topic or a particular area. Right? So you can expand your horizons. All right. Thank you very much. Thanks, Rama, once again.
Yeah,
See
thank
you.
you, Rupesh. In case if any students either, I mean, some of my Tirupati students also joined in the meeting. In general, even if any IIT Madras students might be interested in very such a similar work, I always wanted to collaborate in much more works with Dr. Rupesh also. Either that side or this side, people can come, and we also look for bright students and committed students to contribute on these kind of projects. If anyone is interested, you can always approach Professor Rupesh or me in any form. Thank you.
Definitely.
Thank you so
Thank
much.
you. See you. Bye, everyone. Thanks
See
for
you.
joining.
Catch you.